and the stuff that we will cover today. Okay, wait. First, the stuff that we're going to talk about. One is the task description. So, what challenge we are trying to solve here? There is a bunch of linear algebra that will basically talk about how we can go about solving the challenge or the baseline for the challenge itself. And finally, fun part, which is the part where we actually put everything together and bring it into a final solution. So, I will go over the task description, and then instead of jumping to the linear algebra, I want to show you guys the demo first. So instead of going bottom up, I want to go top down so that it makes a lot more sense. Because I realized while developing the slides and going through it at the end, nothing makes sense if you don't understand what the big picture is. So first off, CNNs are fantastic. They extract a vast range of contextual information with a very small set of pixels, right? The number of, not a small number of pixels, small number of neurons, so they are very efficient, and they generate a latent space. Once we have the latent space, we transpose that into a flat vector, and that flat vector is basically converted into an MLP, and that MLP is transferred through all sets of, through a bunch of convolutional dense layers, until we get to the final prediction stage. And then the final prediction stage will basically tell us what class it is, right? So they have these CNNs have one critical flaw. So let's say, just out of intuition, right? Do you think that a CNN trained on the distribution of the left, so just not a single image of 5 but like a bunch of 5s, and 4 3 2 1 the MNIST data set, and then another one on a bunch of planes, and another one on this mountain, right? Should the CNNs trained on these left images be able to classify the right image, right? Ideally, it should or should not.
Sure.
Should.
I mean, what if you have 8 and infinity?
What's up?
What if you have an 8 and an infinity?
Oh, fantastic.
Edge cases.
Yes, and that we will get to that as well in the demo. It's awesome, fantastic that you brought that up. So yes, for the MNIST challenge, even if you look at numbers like 6 and 9, it does not make sense for it to be rotation invariant. But if you were to look at the cases like this aircraft, right, we definitely want it to be detected regardless of the orientation of the aircraft. So yes, we do definitely want it to be resilient to the rotation of the image, but in actuality, that doesn't happen, right? All of these images were misclassified when they were trained on a standard MLP. So how can we fix this? One solution is data augmentation. So you want to basically take the one image of the aircraft and give it a bunch of say 8 different rotation samples and train it on that. So the model basically learns that whatever rotation it is, it needs to work, and it needs to classify it correctly. But in real life, that is one cumbersome, takes a lot of training time, because if you have a terabyte large data set, your data set just became 8 terabytes in size. You may process the data augmentation in real time and not have to store 8 terabytes, but your model is still training on 8 terabytes of information, which takes 8 times longer than just training a regular regular network, right? The second option is G invariance, which is a lot more fun, where we basically define a neural network to take or like to contain a latent representation of the original image that they get, and that latent representation should be the same regardless of the orientation, right? This is assuming it falls under the definition of a group, which we'll go into in a bit, and that's basically the abstract algebra part, right? We will explore a rotation invariant solution for an MLP today. The problem that we talk about with CNNs being rotationally rotationally robust, we solve that using G equivariance as well as G invariance. Is basically a combination of the two, where the filters are G equivariant and the flattened MLP section is G invariant. So that is a bit more advanced, so we'll probably cover that at a later date. For today, we would establish a baseline with your G invariance with an MLP, right? So before we get to the algebra part, I want to talk about the high levels the uh, for the G invariant MLP, right? Your standard MLP would basically take the input, right, 784 pixels. So we would have an input with input as the number of images that we or the number of examples and the number of features, which is in this case 784 pixels, right? You would then pass that into a convolutional layer, and you would get your final convolutional fully connected layer, and then get your final outputs. Okay, in order to make a standard MLP G invariant, what we do is we pass the input through a G invariant layer at the very beginning. This G invariant layer develops a latent representation that is the same regardless of the orientation, and then from there we just use a normal fully connected layer and get ourselves to the output. This normal fully connected layer does not have to be G invariant because it is a latent space, and assuming the first latent space is the same, everything else following that would also be equivalent, because it's basically saying these four images or these four orientations are one and the same thing, are effectively the same image. Okay, so moving to the demonstration part, uh, this please do not lag. It's transferring data from localhost, but it is still so slow. My computer is dying. Okay, so this G invariant representation notebook was taken from Professor Ribeiro's class. So he owns the copyright for much of this. I basically just hacked together two notebooks to create this example. So I will start these helper functions real quick, and over here we define this standard MLP, and this standard MLP is our general or like our normal neural network, right? There is nothing special about this. This cell block will start training the standard neural network on the MNIST dataset, right? I won't run this now because that would take us some time, a couple of minutes, but just to save us time, this gets about 94% accuracy on the test, on the training as well as the test data set. The test data set over here in this case is in distribution, so we are not rotating it yet. So we have the G invariant MLP, which basically contains the MLP layer before that, and this is just the architecture for that. We have this, and then this cell block after that is just going to train it. Okay, so getting to the example part of things, I will load these trained models already saved into memory and pull out a random image, right? So in this case we get 5, for example. uh, one one would probably be rotationally invariant anyways because it's exactly the same. Let's try 3 for an example. Okay, so over here I apply the single vector transformation, and oh shoot, sorry. Okay, I guess we're doing 7. Okay, going to this cell, I apply the transformation and I will show that, and this is basically just a matrix multiplication that is done on the original number, and then that will generate our final output rotated number, right? This importantly is not me rotating the image using something like matplotlib. It is me performing a matrix multiplication that rotates this image. Now if I were to predict it, or I get the predictions, right? This predicts the number. Well, this is actually rotationally. Okay, it works even on the rotated image. That kind of sucks. Okay. Yes, I might. Okay. Alright, let's try 4. Okay, again, rotated image. Try this one more time. Hopefully, it gets the correct. It predicts the image correctly, and the rotated image it predicts it as a 7. right? Let me just confirm. Yeah, it is predicting this as a 7. This is incorrect. Our G model or a G invariant model predicts this as a 4, and the rotated image also is predicted as a 4, right? It is exactly the same. So the cool part about this is actually if I remove the argmax over here and get the final sort of the final latent layers, right? And this predicts a 4, this predicts a 7, and we see that the predictions are like the predictions you would basically pick out the maximum one, right? This is not, I have not run softmax on this. The final layer is not softmax run, so it's just random numbers. But it remains, but softmax, the way softmax works is if you just want the best output, we can just argmax it. So I basically didn't bother with that. So we do that, and we see that the representations that we get at the end are completely different, right? And over here the representations are exactly the same, like the numbers do not change at all. And that is sort of the interesting thing about this, because in the above case the numbers changed entirely, and over here the numbers are exactly the same. The since the representation was completely G invariant, it was able to identify or get the exact same outputs at the very end. So that was sort of the cool thing about this. So it's not just enough that it is predicting 4 as the highest percentage, it is actually getting the exact same representation in both cases. So that is that. Let's sort of explore how the process of this works.
Yeah, ask questions now.
Of course.
Okay, what happens if you like translate it by like 5 and then rotate it?
It will be so if you translate this by 5, this the representation will be different. It will be similar. It will still predict the number 4 over here, because CNNs are resistant to translation, right? So they're not G equivariant, which means it if we perform a pixel shift, the representations will not shift by a same degree. It will shift by a similar degree, which is why it is resistant. If we push it too far, there is a good likelihood that it is not able to recognize it correctly, right? But in this case, there is a very high likelihood that the predictions, the numbers that we get over here at the end, will be similar. It will predict 4 with the highest, so it was 4 0 1 2 3 4, yeah, okay. So it will end up predicting 4 at the end, but the numbers will not be exactly the same. If this was G equivariant and rotation invariant, then it would be the same.
So, I guess you want to explain this later, but why
Yep.
does it matter that it's a matrix multiplication?
Oh yes, because this relates to the definition of a group. So the reason why this works is because we sort of rest on certain axioms that are defined within a group. So I guess that probably gets to the group section, right?
Yeah.
So getting started with the linear algebra. Are you guys familiar with the group?
Kind of.
Kind of. No. Okay.
No, I am.
So a group is a set of elements G, right? We define that as a variable G, and it contains a certain set of
Oh,
properties.
it's double a semi-group.
What?
It's double a semi-group.
Okay,
No, I'm not joking. That's like actually what it is.
that is cool. I don't know what a semi-group is, but I guess I need to look that up. But a group, consider this as a sort of data structure, but for math, right? And it is a set of elements G. So it is just a regular set, and it contains the following properties, right? It has an operator that is a linear combination of the two elements. The operator is abstract, so it could be addition or multiplication, division, subtraction, anything. So any operation. So we take two elements. Let's just say G belongs to the set of real. G is contained within the set of real numbers, right? And 1 plus 1 is equal to 2, and that's an operation, for example. And it combines it. That's basically what a group is, right? The next operation is, or the next axiom is that a group is closed under operation. What that means is that the elements G1, G2, and G3 should all belong to that set G, right? So if we were to take a set of elements G as 0 comma 1, right, and we do 0 plus 1, and let's take the operation as the dot, right, or like the dot operation over here as plus. We can do 0 plus 1, and that will give us a 1. We can do 0 plus 0, and that will give us 0. So it's closed, right? But if we do 1 plus 1, in that case we get an output of 2, and 2 is not defined within our set G, which is why it is not closed, right? If we were to define a group that contains this operation, we could maybe switch the operation from an addition to a multiplication, or we can maybe set it as define this group as an infinite group that basically contains every element within real numbers. Then it is defined, because however higher number you do, it will still on addition or multiplication belong to the set of real numbers, right? Next, inverses always need to exist for a group. So in the case of, or more specifically, whenever we basically take two elements and the linear combination of them must give us the identity. The identity is basically an operation that we can do to that we can provide to an individual element, and that will not change the value of the element, right? So if we say 4 times 1 is equal to 4, the times 1 did not change the value, right? That is an identity. So inverse of that should exist, which means if we were to define a group with 4, 1 over 4 also has to exist, because 4 times 1 over 4 will give us our identity element, which is 1. So there always exists an identity, which is what I just described, wherein we get the same value when the operation is done. For addition, that would be 0, right? And if you want to get the inverse of an addition, we would just basically just get the negative. So 1 and minus 1, that would give us the inverse. Minus 1 would be the inverse of 1, and 1 would be the inverse of negative 1. Next, the operation has to be associative, which means G1 times G2 times G3, regardless of the parenthesis, the operation should equate, right? Finally, there optionally it can also be a commutative group in the event that the elements are commutative, and this holds true for multiplication and addition. But if we perform something like matrix multiplication, this may not necessarily be the case. If it is commutative, then the group is called abelian. Why is all of this important? And this relates to the question that you had. These 5 axioms are those that on which we define our solution to this rotation problem. We basically extrapolate from these properties or these laws that we know, or we define working under the assumption that our images are a group, right? And only if it exists within this group will those properties hold, and will the latent space be actually invariant, right? If we define an image with a transformation that's outside this group, it will not be invariant at all, and the output that we get will be completely bogus and it will be useless, right? We cannot do very much with it. Also, at any point in time, if you have questions, just shoot, don't interrupt me.
So a monoid is a group without an inverse.
A monoid is a group without it. Yes, that's what I was telling you. So I when we did the first reading group on abstract algebra, we covered groups, rings, and fields. And under groups, I spoke about monoids being partial groups wherein they do not have the inverse, was it?
Yes,
inverse, right? Exactly. So yeah, that was a funny moment for me, because I did not realize that we had covered this until I spoke to you about it and looked back on the lecture, and I was like, holy shit, I have covered this. And yeah, my memory is horrible clearly, but that sucks. In any case, this is a group. Does this group's data structure or abstract algebraic structure make sense? Yes? Okay, sweet. Now we sort of extrapolate on our group, the definition of the group that we have, and we talk about the general linear group, right? The general linear group is kind of a specific type of group where we define the operation as specifically matrix multiplication, and the type of the elements within this group is a n by n matrix, any dimension basically, with the matrix product as the defined operation, as I mentioned. And this matrix operation, the elements within the matrix can contain or are contained within the set of real numbers, right? We can define it to be contained within any sort of set, so it could be complex numbers. For this case, we're just going to keep it simple and handle real number, or talk about it as in the aspect of real numbers. Also, images are real numbers. We do not define complex images, so there is really no need for us to define matrix or the set of complex numbers within the matrix domain. So we can visualize our training data set containing the inputs x, and x belongs to the set of real numbers raised to 3 and or real numbers within the domain of 3 and square, right? And those are the dimensions of the vector. And the reason we define it as that is because we have the n by n image, which is 28 by 28, and we have the 3 dimensions, which is RGB, right? So that is an example of an image. For MNIST, we don't have the 3 color dimensions, we just have the 1 grayscale. So in that case, it will be just n squared. The GL, or the general linear group of 3n squared, in MNIST case n squared, is just the thing. So we basically just input this from the general formula to the formula of the images within our data set with the dimensions 3n squared. Now we define transformations within this group as the operations that we can run, right? And these the only restrictions for these transformations are the axioms of the group that we discussed in the previous slide. So this general linear group is our set of images, and we can perform a certain set of transformations on these images. And for these transformations, our representation or latent representation that we get in the MLP is going to be invariant. So to set up the transformations, we define another group called the transformation group. We assume the same prior input of x images, and this belongs to r raised to 3n squared, right? We can define these 2 different types of groups. The first one is the rotation group, where we have theta, and t is just the matrix with theta as 0 degrees, which in this case performs as our identity, 90 degrees, 180 degrees, 200 and 270 degrees. And these rotations are basically set up over here, right? So this T0 is basically taking the image, doing nothing, and just leaving it at that, which is the identity. We perform a 90 degree rotation, 180 degree rotation, and a 270 degree rotation. The same way we define G flips, which is another transformation group where we flip it vertically, horizontally, perform a 180 degree rotation as well as a 0 degree rotation. Hello.
I was sitting outside for like a minute. I just didn't realize this is just us. Anyways, anyone on Zoom?
Nope.
Okay. Oh,
Oh, he left the Zoom?
Oh yeah.
Oh, that's unfortunate.
Yep.
I didn't even know he left the Zoom.
no, B148, what happened?
What's up?
No, B148, what
There was
happened?
no, it was just us 2 again.
Yeah.
Okay, not three.
And there was another group like doing work in there, so we were like, we'll just come in here.
Okay, well, they could have figured it out.
Could have, but
Didn't make sense. That would be so mean. They were hard at work.
Is there a TLDR icon yet?
Yeah. Okay. So this is the interesting part, right? This is the live demo. We have this image over here, right? And we transform this image by 90 degrees, right?
Okay.
We do that, and we just take a general multi-layer perceptron and
Yeah.
run it, and it's unable to predict it with a transform image, right? Because assuming we train it on the images that are just aligned correctly, and we rotate the image, it basically is as though it has never seen this image before.
Mm-hmm.
And if it has never seen this image before, it's
bad.
bad basically. Like
Rotation isn't a feature that the model trains on, right?
exactly, rotation is not a feature that it trains on. Most CNNs are translation resistant, which means if you move it a tiny bit, it still is fine, and the representations are similar.
Yeah.
But rotation, they're completely useless in that case, right? So if we use the MLP and we get this sort of representation over here, it predicts it as a 4 when it is correctly oriented, but when it's rotated, it predicts it as a 7. right? I can add the argmax to make that a bit more clear.
I just couldn't see it before.
Okay, this is the final layer. So I would run this, and then over here we see that the 4, it predicts it as a 4 correctly. When we rotate it, it is now predicting it as a 7, right? But with the gene variant model that we have developed, it initially predicts it as a 4, and then even when it is rotated, it predicts it as a 4.
Okay. Well,
So it basically fixed the problem,
yeah.
right? And that is super cool. But even more interesting is if you remove this argmax property and look at the final layer, right, before like the predicted model, you see that the outputs that it gets are exactly the same, right?
Yeah.
It's not similar. It does not it doesn't predict 4 just because the probability for 4 is registered as the highest. It predicts it as 4 because 4 is the best option that you can 4 is because it is exactly the same as far as the model is concerned. These two images are one and the same thing,
Yeah.
and that is kind of the awesome part about this.
Yeah. How the hell does that work?
And that uses a lot of linear algebra. And now if you look at this, it completely is different, right? The results are output is completely does not make
Yeah.
sense. So the reason that this works is because of some group theory. But the high level for this, or the top down for how this works, is that we add a G invariant layer, okay? And this G invariant layer basically generates a latent representation of this input, or we basically get an invariant subspace. Our weights are are in the form of an invariant subspace in which
What
it
does
is
invariant
basically
mean? That's a
invariant means that it just does not change.
okay.
So regardless of the rotation, the weights will remain the same. So if you look at this image over here, right, we have this representation of the first latent subspace. So the weights as though it is an image, right? Higher weights are darker color. So we rotate this by 90 degrees and we see that it is exactly the same. So when you perform the forward pass, right, the resultant output that you get it's the same. So our goal is basically to generate this sort of latent weight space, and if we can set our weights to follow this policy where regardless of rotation or flips or whatever that we can possibly define within the definition of the group
Yeah.
is the same, then the model is rotation invariant.
So my one question: does any of this have to deal with the fact that there's a finite number of rotations? In the sense that, like, to me, what I intuitionally feel is that
Yep.
it's symmetrical along 2 axes, right? There's 4 sections that are all
Yes,
symmetrical.
exactly.
So does that have to deal with the fact that, like, we have a set number of, like, angle positions? So if we only dealt with 360, then that's just 360 groups that we need to classify it into.
So good, fantastic. So the thing is, the symmetries that we can get are not infinite. So if you perform a 45-degree rotation,
Yeah.
because of the fact that we have a square image and we rotate it 45 degrees, it would basically exit the bounds of the image, right?
Yes.
And we would have to restructure that image, maybe take the top component, put it on the side, but then the image is no longer the same.
Yeah.
So we can only define this invariance for this subspace that consists of these 4 rotations. So 0 degrees, 90 degrees, 270 and 180 are the only ones that we define it for, which is basically what we were just talking about over here. So wait, do you remember the group discussion that we had from the first reading group?
I was not there for that.
Oh, okay. So all right, let's do this.
It's monoid.
Yeah.
Yeah,
Seriously?
it encapsulates the groups encapsulate monoids.
Mm.
So the group theory is basically considered this a form of data structures, but for maths. Okay, so like in data structures, we define a certain set of operations that we expect to do. For example, a stack we can only push and pop, right? Those are the
Yeah.
only 2 operations that we can do. Similarly, in abstract algebra, we define algebraic structures that have a certain set of properties, and those properties are very strictly defined,
Okay.
right? But based on the assumptions that the property holds true, we can perform a series of operations or of kind of that extrapolate on the initial assumption to give us our invariant subspace, and that uses a bit of eigenvalues, eigenvectors, which we will probably get into in the fun part, right?
Okay.
So first things first, to understand the axioms or the rules that are defined within the group.
Mm-hmm.
First things first, a group is a set of elements, right?
Yes.
It contains a couple of is just a normal set. This set can contain matrices, it can contain just real numbers, it can contain complex numbers, right? We reduce our definition from a set to a group based on if it has or contains these following properties. The first one is that we define an abstract operation for the group, right? This operation can be addition, it can be multiplication, it can be anything,
Sure.
right? It only restriction is that it is linear. So it's a linear transformation. It's not a non-linear transformation.
That's fine.
So that is the first. That's the first point over here, right? And the operation, the operator is abstract. G1, G2 is equal to G1, and the linear combination with G2 gives G3. Now, if we assume our linear combination is addition, we can have 0 plus 1 is equal to 1, right? That's a linear combination. 1
Sure.
plus 2 is equal to 3.
And just to make sure, the linear transformation is just saying that each element is translated by the same amount, or is it saying that each element has the exact same operation? Meaning, say raising itself to the power of 2,
right.
each operation does the same thing, but the
That is not a linear operation.
addition would be, subtraction would be,
Yes.
multiplication would not be, right?
Multiplication is okay. Well, if you say G1 product G2, oh, actually, yeah, you're right. So squaring would also be
Squaring, obviously, because that's another.
Yep.
Is, right?
multiplication.
It is?
Yeah,
So-
because it's just addition, I think.
That makes sense to me, because
Yeah,
it's repeated addition.
fundamentally.
To me,
Yeah.
the question would be like, what is the property that defines it as a linear transformation? If I have a set of numbers like 3, 4, 5, 6, and I multiply all of them by 7, that's my transformation, right? They're each, they're not. It's not like addition where each of them are now just 2 greater. Like the new group is now just 2 greater than its corresponding element in the previous group, right? The distance or whatever we change is larger, but the transformation of the operation that you do sequentially is the same.
Yep.
Right.
Right. Exactly.
Is that what makes it linear? Is that the definition? I just don't know.
Oh yeah, that is correct. That's
Okay.
what makes it
So
linear.
it's the operation that's conducted.
Mhm.
If it's the same every time, that's what makes it linear.
Yeah,
Is there
that.
a difference between linear and affine?
I do not know. What is affine?
I mean, affine is
I know. So the transformation over here uses the affine function under PyTorch. I would assume that it falls under linear,
I think that might be synonyms, but I don't actually know.
but I do not know what affine means.
It sounds made up.
It.
That sounds like a plural word. I'm not gonna lie to you.
Dude, you're literally learning groups.
Yeah.
Okay.
Take abstract algebra. That makes sense.
Anyways, next, the next definition for it is that it is closed under operation, which means that the group should be self-contained, right? So, for example, 1 plus 1 is equal to 2, right? Now, 2, if we define, let's actually get a simpler example. Let's say we use multiplication, right? And we define our group as containing 0 and 1, right? That's the only elements that are contained within the group. If we perform operations between the elements, so 0 times 1 we get 0, right? If we can perform 1 times 1 we get 1, and 0 times 0 we get 0, and this is closed under operation because all of the outputs that we get is already within the group. If we do something like addition, we get 1 plus 1 is 2, and that is outside our group defined of 0 comma 1. If we add 2 to the group, we get 2 plus 2 is 4, and 2 plus 1 is 3, and that also is sort of outside the definition, so it does not become closed. If we want to define a closed group with addition, we can use this. What can we do?
So it's members and operation that you will allow into the group.
Yeah.
That's what will determine whether it's closed or open.
Right. The elements is the thing. The operation does not matter as long as the elements are elements within the group are contained.
So then, if I had an operation that was like, say we have 2 and 0, right?
Mm-hmm.
So if it's, let's say that it's addition is like the operation, then it's still closed because it's 0 plus 2 is equal to 2.
Right.
But if it was like we allowed multiplication also be an operation in the group, then it would be 2 times 2 is 4.
Yep.
And that's outside of the group. So the members are the same, but based off the operation that we allow.
Oh, right. Yes. Correct. Exactly. Absolutely.
Okay.
Sorry, I misunderstood what you were saying. So yeah, that second is or like well, third, I guess, is the fact that that the inverse always has to exist, and the inverse of a given element is basically what you is basically the uh, identity. Yeah, like if you perform if you perform a linear combination of an element with its inverse, you get the identity element. And the identity element is basically the element that you can perform an operation against, and it will not change the original value. So 1 plus 0 is still 1, right? In this case, for addition, 0 becomes our identity element because it does not change the original value,
Okay.
right?
Just curious, is this gonna be leading into having an identity matrix? Because that's the identity thing in our images.
Yes, exactly. It relates to the identity matrix, and this property of the identity is basically extrapolated to eigenvectors, because a projection transformation on an eigenvector is basically this operation, wherein the projection operation becomes the identity,
Mm-hmm.
and then the value is exactly the same. And we find this sort of identity in the process of getting the G invariance, which is super cool. So next is the operation is associative. So regardless of parentheses, the result should be the same. So 1 plus 1 plus or like 1 plus 2 plus 3, regardless of the of how you orient the brackets, the output is still 6. So that's basically that. Optionally, it is commutative. So 1 plus 1 is equal to 2 plus 1, and in that case, it is called abelian. Um, the reason that it is important is because these are the axioms on which we define our solution. We extrapolate on these axioms in order to generate the or to basically to define our invariance. If these features did not hold true, the output that we get would be garbage, basically, and it would not make any sense. So we define a specific type of group called the general linear group, and it consists of the group consists of elements as a matrix. The elements within the matrix itself belong to the set of real numbers, and we perform a specific operation called matrix multiplication, which you
Sure.
already know. So the special group over here is basically us defining our images as a group. Okay, and over here x becomes, let's consider x as our inputs, and it belongs to the set of real numbers to within with 3 n squared dimensions. N squared because n is the length, and we have a square image, so 28 by 28, and 3 because we have 3 colors RGB, right? We can define for in the case of MNIST where
And then,
we
like,
just have
an actual project meeting then. So.
see yeah. In the case where we have just grayscale images, it's just n squared, right? So that is our how we can visualize our training data set as a group. Now, so if we were to basically specify this from the general definition of the from the or like the broad definition of the general linear group to our definition with our use case, we would define GL as 3n squared with the matrix of dimensions 3n squared with R as the what is it, the element space, or element space, and matrix multiplication as the operation.
Could you repeat this last part? So what does GL represent, and then why are we doing it with this real number dimension? Like, what are we mapping?
Yeah. So consider the matrix as the single image, right?
Sure.
And the image consists of RGB values. So
Sure, on the
RGB
blue
values
line.
are just pixels, right?
Yeah.
And we represent them as numbers. So that is why we define it as under real numbers. We could define it as complex numbers, but we don't really have
That's
any
cool,
use
yeah.
for it because we don't encode our images as real numbers. We as complex numbers, we encode them as real numbers. So when we consider an image or matrix, this is basically what we are doing, right? It's just a matrix of numbers. That's what an image is. So make sense?
Yes.
Okay, awesome. The general linear group is basically just a specific type of group, and that's where we will focus our discussion on today. So we can define the transformations that can be performed on a group, but the only restrictions are the axioms of the general group, right? So we the transformations that we define are basically the invariances that we will specify, and our model is going to not be affected by these transformations, assuming it fits within the group.
Okay.
So to specify what a transformation group is, we take our same prior input as images x belonging to R and dimension as 3 and squared, and we define these two type of rotations, right? The first one is the rotation group, and or two types of transformations. The first transformation is the rotation group. We define it as with 0 degrees, 90 degrees, 180 to 70 degrees, different type of rotations. We can define another group called the flip group, which has the vertical flips, horizontal flips, 180-degree rotation, and a 0-degree rotation. Those last two are basically to make it a group, because the vertical and horizontal flips by themselves do not constitute a group. The 0-degree flip is the identity element, because if you take a 0-degree rotation, it will just remain the same. We have an example of the rotation group or the rotation transformation group over here, where we rotated 90 degrees, 180 degrees, and 270 degrees. And this is basically done using a matrix multiplication, not by.
Just to make sure.
Yeah.
Does each group require an identity element? I think you might have covered this before.
Each group requires an identity element.
And that's
yes.
the one that it will base all its operations off of? Or just like to have like a... That's something you can check if it's like closed under, right? That's the utility of having the identity element in the group?
The group, the axioms that they define are kind of arbitrary, right? They don't define a reason for why these are the rules of the group. So, like for example, the group, if a group does not have an identity element, it becomes a monoid. That's the technical definition of a monoid.
Seriously, is that true? Whoa.
Yeah, and if it's basically
Actually, it's the inverse. They have the identity element, but not a guaranteed inverse.
Oh, they have the identity but not the inverse.
Yeah.
That's my bad. So if a group contains an identity element but not the inverse, it is a monoid. But if it contains, yeah, right, exactly. But if it contains an inverse as well as identity, it becomes a group basically. So it's abstract, but it's kind of like how we define proofs for anything, right? If you want to prove something, we refer to things that are true and say if this is true, this also has to be true, and then this also has to be true, and then so on and so forth until we build up to the final proof that we have, the final equation that we want to prove.
Yeah.
Right? And if we can only on the basis of the axioms get our final proof, that means that the proof has to be true. That's basically what we're doing over here.
That's really useful in functional programming. Basically, you implement these core axioms and like operations for a type, and you get like a huge library of like things that other people wrote, and that's like, it's basically just making libraries really really generic.
Can you explain that again? So like, I define my data type, right? Whatever int, whatever.
Yeah,
right?
yeah.
Or
So like, you implement like integers, right?
Yeah.
And someone knows that like monoids do stuff and like groups do stuff, right? So they implement like a bunch of functions that do stuff on monoids, right?
And since yours falls under the monoid category,
yeah. So you
implement
like what is the identity element for an int, what is the inverse.
Yeah.
And you implement those like 4 functions, and then you can get like a billion of them, right?
Yeah, because those are all the proofs now that it falls under that category, right?
Yeah.
You can access all that
So
information.
it's literally just like implementing an abstract class.
All that oops slender.
Well, no, I mean in functional programming it's called type classes usually.
Okay, the same idea.
Yeah.
Wow, see, that's really cool.
It's awesome to see the mathematical basis on which the
it's cool to see you utilize, dude.
By the way, once you get to the end of it, there's like an interesting tangent that's related to synthesis, kind of. But I'll wait because I don't really understand it.
Okay. Another thing that is important to note is that these are basically transformations on themselves. There is no intermediate representation. So as I mentioned, like I was saying before, that I'm not using matplotlib or something to rotate this image. I am performing a matrix multiplication that rotates this image. The reason that is important is because this transformation group is there was a word for it, something auto. Not important. The actual idea is that if there is an intermediate representation, there is a chance that your data, like there is no way for you to guarantee that the transformation is still equivalent, right? It can perform some sort of data, like the data could be manipulated in some way. It could be rescaled, for example. It will still look the same to us, but functionally it would have changed in its form, right? So it is technically possible to use something like matplotlib to perform the rotation and then say assume, okay, fantastic, this works, but it is a risk that you take. So it is generally recommended to not do that and just stick to the transformation where it transforms from its type to another type of itself rather than a different representation. So if you were to transform this image to a point cloud and then to then rotate that point cloud and then transform that to an image again, it would still work, but it's just not guaranteed. And in order to guarantee it, we just perform this directly.
You said that the transformations don't happen. Why don't the transformations just happen on the identity element of the group? Wouldn't that be the way that you get the base for all this?
As in?
Meaning, like, you said that the, correct me if I'm wrong, right?
Yeah.
But the transformations can't happen to elements inside the group. They're just inherently like this. I'm not really sure what that means. Like, so let me tell you what I gathered. I gathered the fact that, like, okay, I'm gonna be able to get like an element. Sure, in matplotlib I could rotate 90, 180, right? 270, right? But instead of doing that, I can instead use the transformation that's defined in the group as whatever is done here, right?
Right.
To flip it and do whatever, and that's different because we're just using an actual element from the group instead.
It's different because it is just performing matrix multiplication. So
Sure.
the transformation group, right? What these fundamentally are just matrices, right?
Yeah.
So you can if the matrices for T0 for instance is just 0 1 diagonally. That's the identity matrix, right? And that would not change anything. So the rotation matrix is defined differently with a different linear transformation that rotates every single element. I don't remember what exactly that is. Okay, but wait, what was the question exactly?
So then, each of these are defined as a matrix, and you're saying that the operation is not about the fact that we can just turn the image, but it's more so that these are the transformations. This group has the transformation that we have to use. So, I guess now that I say it aloud, it's not as confusing to me. I was thinking that these are all images that are like stored inside the group, and then I was thinking that if you had if you were storing the operation to transform each element in the group, why wouldn't you just do this as the base, saying like, oh, the original image is whatever the image is times the identity.
Right. Okay.
Matrix?
Yeah, that's my bad. Okay, I should have explained this a bit more clearly. So the general linear group is for the images,
Yeah.
and that is one group, and the transformation group is a different type of group altogether.
Sure.
So we have two different groups that we are working with over here. So the that is why the transformation like the transformation group is basically the set of operations that we can run onto the general linear group that will give us the transformed vectors or transformed matrices. In this case, it is the F image. So that's that. Does it make more sense now?
Kind of.
Okay. So well, that's the end of the boring part. It's cool, but it's yeah, whatever. Anyways, so our idea, right, or our objective fundamentally is to generate a layer, our own sequential layer, right, that on a forward pass behaves in the like has the behavior of this equation, right? So the sigma is basically the activation function. These are our weights. This is x is our input and our bias, right? So these x can be transformed by our transformation group G. So we could say perform a 180-degree rotation, right? This we want this equation to hold true.
Yeah.
Right? And if this equation holds true, that means that our neuron is G invariant, because that means it doesn't care about the output that it gets is exactly the same regardless of the rotation or regardless of the transformation.
Does this require 4 times as much computation because there's 4 different, and there's just example
Right.
rotations. It just means that there's 4 other things it has to satisfy, right? Instead of just one equation.
So it takes some computation to get the invariant subspace, right? But once we get the invariant subspace, which is this sort of thing,
Yeah.
these weights,
Then it can be applied anywhere, right?
yeah, then it's basically just a normal neural network, and the normal sequential network is just defined as this. Generally, the number of neurons are stay the same. So we have 784 input features. Our G invariant layer will give us 784 output features, which in this case is 28 by 28 as well, and that will be uh, subspace invariant or G invariant. So regardless of the shape of the input, if we perform the matrix multiplication, it will be the same. That's the basic goal.
Wow.
So uh, the this is our basic objective, right? Make sense?
Yes.
So we want to obtain this latent subspace, and this latent subspace is transformation invariant. That is our goal, right? At a high level. If the above equation holds, our layer is G invariant, and now the next question is how do we find this? How do we extract this sort of subspace from all of the variables, all of the numbers, all of the different weights that we can possibly have? So we do this using this special thing called the Reynolds operator, right? We can reduce this entire equation down to this fundamental operation where we have T1 and T2 is the operation with the original image, and we get just T1, right? You can consider T1 as our weights, right?
Sure.
T2 as our transformation group, and we want to make sure
X is the image, or is
what X is, yes, X is the image, exactly. Because X will be our input weights, right? X could be anything, but in this case we are defining it as our image.
sure.
So we want it to remain the same regardless of transformation. So it is transformation invariant. So we do this by finding T2, right? And when we find T2, we would basically get our solution, right? And this is formally called the Reynolds operator. This Reynolds operator is incidentally just the mean of all of the groups, right? So if we have the four matrices, right, that define the four transformations within the rotation or the flip group that we define, we just add all of those four matrices up and divide that by the number of elements. So 4. We just get the average of that, and coincidentally, that average satisfies this first equation.
And that's specific to rotation, right?
Yes, rotation or flips, or if you define an arbitrary transformation, it will be invariant to that arbitrary transformation, assuming that transformation falls under the definition of the group.
You also have to like add kind of another like summation to the group because the group doesn't necessarily have an
Group,
addition.
this is like number of groups, number of
Yeah,
elements. I mean.
I'm saying that
Value.
summation is not necessarily defined. For
Oh, wait, what? Fuck. Shit. No.
What did I do?
God.
Can you explain what that means?
Just like a group.
There needs to be G. There needs to be tiny G on the left. Just imagine there is tiny G
Oh,
over here.
well, I mean that's not what I was saying. It's
Oh.
just that, like we have a group, right?
Yeah.
And that group is defined for some set over some operation,
Right.
and that operation is like rotation,
Right.
which is multiplication, right?
Right.
But like to use the summation notation, right? We have to also have addition be defined for those elements.
Oh, no, it does not have to be, because we define the general linear group, right? So for a group only has one operation. It can be any arbitrary operation, but it cannot be two operations.
Yeah.
So it's not addition and multiplication, it's addition or multiplication, right?
Yeah.
But for the general linear group, the operation that we define is not multiplication or addition. It's just matrix multiplication.
Okay.
So when so all of the group, all of the elements within the group are just matrix multiplications with the original image.
Yeah. So you still have to be able to add stuff. Though.
You do not have to add stuff.
But how does summation work?
Oh, okay. Yeah. So the Reynolds operator, this T2 is not belong to the group. This does not belong to the group.
Okay.
So that is why it doesn't have to. That is why it does not have to fall under that particular operation. So okay, but also imagine tiny g over here. Okay, please.
I will. Don't worry.
Thank you. So now, when we extract the left eigenvalues, eigenvectors from T2, the eigenvectors basically define those that just scale, right? It defines, or it finds the basis vectors that only scale and do not transform beyond that scale. So T2 by definition is a projection operator. The Reynolds operator is a projection operator, right? And there is a very serious proof for why T2 is satisfies this G invariance equation and why it is a projection operator, but it is frankly beyond my understanding. So that we basically use those two properties to define the definition, to define the invariance that we
What
wanted to get.
What do the V's represent here?
These are the eigenvectors.
Oh,
V
sorry,
represents
sorry.
V represents the eigenvectors
Yeah.
of T2, and by the definition of the eigenvector, right? We know that V times T2, right, should be equal to a scalar lambda times the original vector, the eigenvector,
Eigenvalue.
right? Since we know that T2 is a projection operator, as in it only updates the projection of the matrix and it doesn't scale it, the lambda has to be by definition 1. So Vi times T2 is always by definition Vi, right? And this is incidentally what we want to do with the equation up top. So we define our output weights, right, as the eigenvectors multiplied by our arbitrary input, right? And when we get our output vectors from this, it is G invariant and it satisfies this equation over here.
Wait, that's kind of
Say it again. Hold on.
So this part makes sense, the last equation, right?
Yeah.
Why lambda is 1 is because T2 is projection,
Yeah.
and this V times T equals V sort of it satisfies this, where if you would say V or over here V times T is just V
Because it's a projection, right?
because it's projection, and then this entire statement now makes sense, right? So if we know that this transformation holds true for the eigenvectors, right? For the eigenvectors, this is correct, right? So when we define our output latent space, we can set the vectors such that the like the input times the set of eigenvectors gives us the weights that we need to set, and this is our invariant subspace. This is the invariant subspace that we were looking to find, because this WT represents this. This is WT, or this is W, more generally,
Yeah.
right? And we just found this using that equation, and by just evaluating that, we get the subspace. And now this subspace becomes the weights for this initial layer, and this initial layer gives us the invariant outputs, and these invariant outputs are the same regardless of the transformations. Then we run this through normal fully connected layers, and our machine learning model is just transformation invariant, just like that.
Whoa.
So still, how do you deal with like 6 and 9?
6 and 9 you do not deal with it. Like it just does not work.
Cry about it.
Yeah.
Is it like 50% confidence in each, basically?
Yeah, exactly. And if you look at this over here in the training for the live demo, right? If you see the accuracy score of the MLP, this is at about 94%. But if you look at it for the it's not there. Okay, it will take a second, but this is about 60 to 70%. And the reason for that is because of the fact that the 6 and 9 it basically is confused with, because it considers it exactly the same thing.
But I feel like the accuracy shouldn't be that much lower, right? It should be basically 6 and 9. It should be 50% correct for each, right?
6 and 9 it should be 50% correct for each. It changes, it's give or take really, but you basically consider those two useless. If you were to define like a line like that,
Yeah.
how you have in those Uno cards that defines the orientation of it, that would fix the problem, and MNIST would be exactly correct in each case. We can also make, so this is 70% on the first epoch. I would assume it gets a little bit better, but the idea is basically just that you keep training it, and if you complicate the MLP, surely you would increase the output, because currently this is just a single layer MLP.
I still feel like it should be at least like 75% accurate,
Yeah, well, it will get to 75% accurate.
Because that means it's like even if it's 0% accurate for 6 and 9, but it still retains the 95% accuracy for the rest.
Mm-hmm.
That would be 75, right?
I'm not as good as math as you are. My
Dude,
ZFX
I'm
score is bad.
terrible. Mine is worse.
I did it today. I didn't break 40.
Dude, that's still fucking way better than me.
Okay. Anyways, this is the whole thing. Then this will ensure that we build a feature space over here that is invariant to rotation, and this is the
I
demonstration, and that's basically it.
I guess the explanation for that is that it might use the rotation, like it might somehow be helpful to